Hello, everyone. Welcome to this latest episode of whatever it is we're calling what we're doing here. If you're new here, my name is Jared Overson. I've been running these streams over the course of the past several weeks to go about basically showing people how to deobfuscate and manipulate JavaScript in crazy and weird ways. We've been using the lovely obfuscator.io JavaScript obfuscation tool to give us a foundation of obfuscations that we can deobfuscate. Now, obfuscator.io and JavaScript obfuscator is something that you will find in the wild, but even if you don't find these particular obfuscations, the strategies here are easily transferable to a whole bunch of other obfuscations. Let's see here. So if you want, I have pasted the GitHub repository in the chat so you can follow along. Although this next stage is going to be using a library that I've not released yet, so it might be more of a visual thing right now. But you can check out the other stages and see what we're doing here. So let's say like stage 3, this is what we generated. So this is what the obfuscated, let's see, this is what we start with. Basically, it's just a greeter class. We take in a target. When we greet, we console hello, the target, and we can change the target. Nothing too exciting, but our obfuscations are done in the obfuscate.js. This does a lot of weird stuff. This is what it ends up looking like. You may have seen code that looks like this in the wild. This initial array of escaped strings is pretty common, and a number of obfuscators do this. So seeing this alone is not an indication of JavaScript-obfuscator, but it's the same style of obfuscations. But then we can deobfuscate it with our deobfuscation program right here, which is 59 lines of stuff, and we can get this at the end. So the strategy here is to really just take JavaScript and use static analysis and transformations in order to transform it into something that is easier for us to manage. There's a lot of security code and malicious code and even just normal company code that goes through obfuscations like this. And when you want to start digging into them for the purposes of automating a website or bug bounty research, stuff like that, you're going to want to dig in and take control and find the hooks that you want to touch in order to, exploit things, for lack of a better term. So here we have one more obfuscation in JavaScript-obfuscator, and that is the dead code injection. But before we jump into that, I will show you what I've been working on this weekend, which is a JavaScript partial evaluator, which will take in a shift formatted AST and allow you to step through the execution of this code in order to evaluate JavaScript in pieces. Now you can evaluate whole chunks of JavaScript, but the point of me building something like this and not reusing something else, aside from us focusing on the shift AST, is so that I can selectively choose what I want to execute, which means I want to jump around in the application and I might not necessarily want to execute an entire blob of JavaScript. I want to parse it, analyze it, figure out its scopes, figure out where all the variables are, but then just execute like 1 or 2 lines in order to find the value of something that I want to extract, or to determine whether or not a block of code is going to be run, and if it's going to be run, how is it going to be run. This is certainly a substantial chunk of code, and I did not intend on building this at this time. I just woke up at like 3 o'clock in the morning one day because kids, and couldn't get back to sleep. So I started just busting out a loop around AST nodes just to see how far I could get. And it's been just a weekend project for the past weekend, over the holiday weekend. And now it's actually, I'm pretty impressed at where I'd gotten, because I am not an interpreter writing sort of guy. So it does a lot of things reasonably well. There's a whole bunch of hacks in here, but it works for what I want to use it for. Let's see. So a lot of the tests are just basically asserting that the behavior of the shift interpreter is the same as the behavior of eval JavaScript. So we test loops here, making sure that we can run basic loops, make sure that we can we support break statements, continue statements, while loops, do while loops, stuff like that. So what this allows us to do, and I'll show you kind of right here, I copied and pasted some of our obfuscated code. It allows us to basically throw this into our interpreter, analyze it so that we can figure out all scopes properly, and then just evaluate the statements that I want to evaluate in order to find the resulting value of one of these statements. So if you remember from the last episode, we were trying to deobfuscate the control flow flattening and manipulation of JavaScript-obfuscator. So we were trying to figure out how to find this data structure, how to find while statements that matched this shape, and then finding this variable declaration statement right here, and then extracting everything out and running our own code in order to split things around. Now what we can do is just take this out, or well, not take it out, but reference it directly. We're evaluating that right here, and then we are popping over to here and evaluating that. And then we are getting the variable value of whatever, let's see, variable value of binding. This. We were getting the value of whatever h ended up being. So this dramatically simplifies our deobfuscation code for this particular type of obfuscation, because we don't actually need to care about the internals of any of these things. We'll just execute it and figure out what it comes back with. So I will be working on this until my motivation wanes. It's already in a reasonable spot, but I want to clean it up a bit. And then we'll incorporate it into some of our deobfuscation techniques going forward. I'll try to probably use it right now in our dead code deobfuscation. So if you are following along, all we're going to do is make a copy of stage 4, call it stage 5. Let's see, we're going to want to obfuscate here. Default obfuscation options. We're going to want to turn on dead code injection and set the threshold to 1 because we want to see what this actually does. Let's see. So everything else is off. Let's turn on some dead code injection. Let's hope this works. I feel like we tried this last time and it didn't work, so we need to get some more complicated code. But let's see. All right, so stage 5, node obfuscate. Let's see what we get. We do get stuff. Okay, yeah, this is more than I expected. So our original here, we added a bit of stuff last time because we were doing the control flow flattening, so we had to make the code a little bit more complex so that it would just have more to work with. So the code we're obfuscating right now, basically it's the same sort of thing we were just looking at, except we added more console logs and had a few branches for different targets. So now our obfuscated code, we still have this array up here, which for the sake of learning and figuring out what's going on right here, let's see if we can get rid of that. String array false. I would have expected that would not have that. We in the right directory? Stage 5. Let's see. Array. Rotate string array, string array, string array encoding. String array is true there. Default. So we are rotate string array, dead code injection. All right. Well, we have those obfuscated for some reason, or we have those extracted here. So we have WFFPZ. I wonder what that is. So we have our string array right here. That's unfortunate. I feel like that we turned that off last time. Dead code injection. String array. Let's see, default obfuscation options, string array threshold. Let's do that 0. Node obfuscate, original obfuscated. Same thing. Oh well, I guess this is what we'll work with. All right, so maybe this is just this is an artifact of the dead code injection. Maybe it forces this string array up here. I don't know. All right, so we have our constructor right here, which if you remember our constructor was extremely simple. So now our obfuscated version has a bunch of gross stuff in it. So we have if b 0 essentially is not equal to b0. Well, I mean, that's just, well, assuming that this doesn't do anything strange, that is obviously going to be false. And then this will be run. But now what we can do is use our partial evaluator to actually just figure out if that is false. How cool would that be? Ooh, interesting. Oh, we could just eval that whole thing. Ooh. All right, let's see. Let's see if we can wedge our interpreter in just now. All right, so we have our original, we have our deobfuscate. So we have our shift AST. Let's see. Const interpreter is what I want. Equals require shift, let's see, shift interpreter. Let's see if that actually works to begin with. Oh, let's get rid of all this right now. Oh, no, I need some of it. All right, so we have the shift AST. I'm very likely going to need that. If you have any questions on ASTs and stuff, JavaScript in general, if you're new to this stuff, then feel free to ask in chat, and I'll answer as I can. ASTs are somewhat terrifying looking beasts, but once you start playing with them, they become a lot easier to understand. All right, so we have our AST there. We have our refactor session. Now what I want is to get our, so we have our interpreter. So I think I can just get interpreter, and then I need to interpreter.analyze. Do I need to pass it source? I just created this, and I forget how to use it. So index, we get our interpreter from here, constructor, context options, and then we analyze the script. Okay. Or we just pass it to there. All right, so we have our interpreter, we get a default context, interpreter.analyze. I think I'm going to need to pass it the AST. I just looked at this. Script, yeah. Yes. JavaScript obfuscator. Where am I? Deobfuscating JS streams. All right, so we have an interpreter analyze, and now our interpreter is set up. Now we need to figure out how to get to the nodes that we want to evaluate. So let's see here. We have our original obfuscated. Let's see here. We want to evaluate the first one. We want to evaluate both of these. Let's hope this actually works. Okay, so we want to evaluate the first two statements. Deobfuscate. Interpreter dot evaluate AST statements 0. Oops. Interpreter dot evaluate AST statements 1. So now we have I need to get rid of some of these other windows. JavaScript obfuscator we don't need. Shift interpreter, I'll minimize you. Shift refactor, I do not need you right now. All right, so we have evaluated the first two statements. What that will give us, let's get rid of all these things. Close others. Original obfuscated. So that'll get us this variable populated in our evaluator and this variable populated in our evaluator, so that we should be able to call, or we should be able to execute this expression to determine its value. Okay, so we have that. Now let's see if we have, okay, so interpreter dot, let's parse our own AST and see if we can run that. I'm using my library in a way that I have not used it before, so let's see how this works. So parse script. So we have a variable b, and we want to call, let's say, b0. Let's see what we get out of this. So that's parse script. So now interpreter.evaluate AST2 statements 0 const b console log b. There's a whole bunch of nodes that I have not implemented, and I think I've implemented. So I've implemented function expression, binary expressions, computed member expressions, and return statements. Those should all work. And let's see what we get here. Process dot. Node deobfuscate.js. Cannot read property of children. Oh no. That's because I've parsed this script. This node does not exist in the other tree, which means I'm not going to be able to do that. That's a shame. These still have worked properly, but I can't just parse arbitrary scripts and shove those in. Oh well. So now let's see here. So let's get our expression that we're looking for. So we have AST Explorer. So we want to get the first if statement in the constructor. So we have an expression statement. We have callee function expression, body, class declaration, elements, class element, method, name, constructor. This is what we're looking for. So we want to get the first statement there, and we want the test in there. So what we could do is we could swipe the constructor with our query. So const constructor equals refactor.query. Let's see, we want to get a, what is that? Class element. We want a method with the name of constructor. So method, actually we can use our shift query. So let's get our JavaScript over here, query. So we want a method, I think. So let's get all the methods. All right, so we get constructor right here. So we want a method with a name.value equals constructor. It's capital C. Cool, that gets our method. So now here we have our method. Let's grab the first element out of that list. Now what we'll need is the first statement out of there. So const so the expression is the constructor dot body first statement statements 0 statements 0 if statement test, right? Test is what we're looking for. So we have our first statement, and this should be the expression we're looking for. Let's check that out. This is not going to be needed anymore. Cannot read children of undefined. So interpreter deobfuscate line 17. Huh. So I was mistaken about that original error. This is going to be disappointing. It is not working on this particular AST. So we have an analyze. AST statement 0, AST 1. So where was the error? 17. So the first statement here could not be evaluated, which is just an, oh. Well, this is going to be disappointing. I have not, I'm not sure where the error is coming from, but what I do know is that I have not implemented array expressions yet, which is certainly going to be a downer when we're trying to assign an array expression to A. So at this point, we can deobfuscate via different methods, or we can work on the interpreter in order to flesh that out for array expressions. Anyone have an opinion as to what we should do? Outside of evaluating this stuff, let's see, original obfuscated. So outside of evaluating this stuff, I mean, we could eval portions of it, which is, I mean, going to be doing similar work. It's just going to be contaminating more of our local environment. What we would have to do otherwise is go through and extract these values out and kind of hard code the replacements. Well, first, I guess we'll get rid of all these B's. Oh, and if we do that, okay, no, we can still work with this. So if we do that, then we'll get rid of all the references to the call expressions to B. And then what we'll have is a binary expression comparing two strings, which we should still be able to evaluate even without even doing anything here. So this is going to be throwing back to some of the stuff that we did in stage 1. So it should be relatively easy. Let's see what we got here. All right, well, let's get rid of our interpreter for right now because we don't need it. Let's see, let's get rid of everything right now. We don't need traverser or interpreter. Let's go back to stage 1. So what we did here is we sucked out the original array expression into these strings, which we can still do here. So we have refactor. Let's see, console.log strings. Okay, still got our strings there. So these are, for people who've joined us, this is using the shift refactor library, which is a bunch of like sugar functions that you can use to manipulate shift-based JavaScript ASTs. And one of the things that it exposes to you is the query method from shift query, which allows you to write CSS-like queries for the JavaScript AST. So what we're doing right here is looking for the first child of script, and we want the array expression therein and the elements of that. So if we take that over to our shift demo, throw that in here, or shift query demo. That is not what I expected. Script first child array expression elements. It's, something is broken here. All right, well, that might be a broken web app. Oh, well. So what we have right here is the literal string expression, the array of literal string expressions that we can see in ASD Explorer here. So if we go to the variable declaration statement right here, we go to variable declarator, we're looking for the array expression, and we're getting the elements out of here. So this is what this is. And because it's a list and because it is the same order as these elements, we can operate on this list however we want and then just generate the code out when we need it. All right, so now we have our strings. What we need to do is, so we got the destringified declarator here. This code right here from stage 1 selects the variable declarator that has the binding name of B. Let's see if this works on our shift query demo. Oh, we don't have the right source in here. That will be a problem. So the variable declarator that has a binding of name B grabs us this function right here. So now we need to get the offset that it is working with. The offset is this value right here, which we don't actually technically need because it's 0, but we use this in our stage 1, so we might as well suck that in right here. All right, so now we have the destringify offset. Now what we can do is, so what we've also done here is we've renamed this variable to B. So let's see what that looks like here. So see, this is the printed out generated code. I see that all those B's have been renamed to destringify. That was mostly just an example for earlier, but what this means is that it makes it easier for us to select that in the future. We can just select any identifiers that have the name destringify, and then we know we're going to be getting what we wanted to get. So now what we want to do is replace all call expressions that have the name destringify and replace them with the literal string expressions that we have extracted up here. Because what this function is doing is basically it's reversing or accessing all the extracted strings from this array, and I mean that's how the strings are extracted. So what we can do is replace all the call expressions for that function, parse out the arguments that it's being passed with, and then grab that element of the array, and then just substitute the literal string expression from that array into the place where the call expression was. So what we're doing here, we're grabbing all the call expressions. Replace just goes through, queries this, and then passes each node to the function like this. And what we're doing is creating a new literal string expression, which is just probably what you would expect. It's just a string value in JavaScript. And the value of that is going to be we're going to be accessing the strings list up here. And we're going to be looking for the first argument of the node that's being passed, which is this, all over the place. And we're using that as the index, minus the offset, which in this case is 0. Like I said, it's not going to do anything, but good to have just in case that offset changes. So now, what we should have done, ooh, that's a weird song. Okay, so let's bring that around. So refactor.replace, let's see what it looks like we got here. Cool. So now we have all of those calls to B/destringify. We have those replaced with the literal string expressions from the array expression at the top. So now what we can do with the sugar function here is convert computer to static. And what hopefully this does very nicely is make everything easier to read. So now we have a more, a saner bunch of JavaScript to deal with, and we don't have all these calls all over the place. So now let's see if we can get that interpreter to work properly now that we have simplified code. Let's see here. So first I want to, because we have no references to this array or this function anymore, I want to get rid of these two things. So refactor.delete AST statements 0. So I want to delete the first statement and then the first statement again. Basically, we're just kind of we're shifting the statements up, and let's hope this works without breaking. Oh no, what happened? AST statement 0. Why did that break? Oh, wait a second. No, that should work. All right, let's check our AST Explorer again. So let's get our new code. Node, oh, we're doing obfuscate, that's why. Okay. No deobfuscate. Cool. That does work. So now we've gotten rid of our array string at the top, and we have gotten rid of our destringify method and replaced all calls to that with the resulting literal string expressions. So now let's see if our interpreter works. Const, and it very well may not. This is very much a work in progress. It works in my tests, so whatever I'm doing here, I need to add to my tests. Because this is substantially more complex than I was writing tests for. So we have our interpreter. We have our AST, which has been manipulated, but should still be okay. So const interpreter equals new interpreter. Let's see here. I want to interpreter.analyze our AST. Let's see if this works. Might not. Cannot find module shift interpreter because it is not a real module. That's not an npm installed one. Okay, cool. Well, that at least works, which is good. So the analysis works. Now let's see if we can analyze a simple expression like this, which it really should have no problem with, but who knows. Interpreter.evaluate. Well, let's get. Ooh. What we could do is find all binary expressions that are comparing two literal string expressions and then just replace them with the Boolean. That might be okay. Is that okay? I mean, that doesn't really get us much. It makes our code a little bit easier to understand because we're not doing these comparisons everywhere, but it doesn't really get us much. That actually might not be that bad, because then once we've replaced all of those, then we can do a sweeping replacement of all branches that are definitely not going to be run, which are just, I guess, easier for us to see because we'll have replaced everything with false and true. All right, let's work with that. Okay, so what we can do is then look for all if statements. So we want an if statement. We want all the tests of if statements. If statement dot test. So we'll have all of these here. Some of them we're not going to be able to do because it looks like some of them do need some further evaluation, but we'll wing it. So refactor dot replace gets us all the tests. Node all right, so we want to test to see if we are dealing with two literal string expressions. Or we could just actually test to see if we're dealing with two literals. Because if we're dealing with, just comparing two literals, then that is easy for us to do. Okay. And it won't matter we won't need to worry about the operator being used, because if we're just dealing with two literals, then we can just replace the result. We can replace the node with the result. All right, so if node that, I missed TypeScript. Node.left.type call expression. In our case, it's going to be a literal string expression, or it's going to be literal something. So node.left.type.match literal. That feels ugly. I feel like if I were doing this in TypeScript, I would have a fancier type involved, but I'm not. So if node.left.type.match, so we want to, so both the left and the right side of the binary expression should be literal somethings that will also capture literal regular expressions, but because of our code, and because regular expressions are probably, literal regular expressions are not too common to be found in binary expressions, we don't need to worry about them here. We're hacking. We're figuring out what works. All right, so let's see if this actually works okay. So this is going to not do anything. So we're going to just see what we get here. All right, so we're getting nodes. We're getting more than I expected just by eyeballing it, but that's good enough. All right, so interpreter.evaluate node. Let's see what we get here. Will it work? What do you think? I don't think it's gonna work. Dell, why are you doing this? Wow, I cannot read property children of undefined. Why do you have this problem? That sucks. Well, I clearly need to add some tests to my interpreter. That's a shame. Well, because we're dealing with simple stuff here, we're only dealing with not strict equal and strict equal. We can do that ourselves. So if node.operator equals return new shift.literal Boolean expression. Does that need a value, or do I just pass in the value here? I don't know. We'll see. And now we will match the raw values of the literal nodes to each other based off of strict equal. So value equals node.left.value. Is that what we have? So I mean, this is not what we should be working with. Hold on. Let's get our proper code. All right, if statement test. So we're doing here, we got a left literal string expression value. So our left is, so node left.value, triple equal node.right.value. Else if node.operator equals let's see if we have, this could have been a little bit terser, but let's see what we get here. Yeah, cool. So we've replaced all simple comparisons with true or false. So this will make it incredibly simple for us to identify which branches are just they don't need to be run. So we can now grab all if statements and then determine whether or not their test is true or false. I'm guessing probably a lot of these are false. Since oh no, so if true. So if true, hello target world. So this target equals new target. Oh, interesting. Let's go back over here and check this out. So let's check out our original code. So original over here. So this target. Let's see, original obfuscated, or not where we are. So this right here, this code does not exist in our original JavaScript, or it does not exist here in Greet. Greet is just this. So the dead code injection actually does it adds code from other parts of the program into the dead code blocks, which, I mean, that's clever. It makes it more plausible. It makes the code look more plausibly able to be run. but let's get rid of it. So let's see, original, deobfuscate. So now we want to replace, we actually, no, that's all right. I was gonna say we don't have to create these literal Boolean expressions up here. We could just do everything in this one. But this is not a bad strategy because this would allow us to have a few passes at this replacement of the branches in order to all distill them down to a true or false. So it'd be easier for one replacement to just sweep through and nullify all of them. All right, so we have our if statements. So this will get every if statement. Now I want to get a test that is just a literal Boolean expression. So if node.test.type equals literal Boolean expression. Okay, so we have a literal Boolean expression. If it is true, then we replace this node with its consequent. And if it's false, we replace it with its alternate. So we have those, let's see, if statements. So we have two, let's go to ASC Explorer. Let's get our new code. Whoop, I've got a few of these up. All right, so we have a function expression, statements, variable expression, class declaration. Let's go to our second element, method, body statements, if statement. So we have a test and a consequent or an alternate. These get run depending on the value, or the return value, or the resulting value of the expression in the test. So if we have a node.test.type literal Boolean expression, we should get here, we don't have our code here. So we should have a value in the node. So if node.test.value, then we can return the block statement. Or it could just be an expression statement if you don't have the curlies around it, but we can just return it no matter what. So node.consequent else return node.alternate. Let's see what we got here. We have that, that's okay. No, invalid return type from replacement function undefined. Because I did not return the node here. Cool. And it looks like we have indeed gotten rid of a whole bunch of code. We got rid of all of it. No way. That was much easier than I expected. So we do have these ugly little block statements over here. So we could replace all block statements that only have as one child another block statement just for cleanliness. And you know what? We might as well. So replace, let's see if we can grab just the block statements that have a block statement inside. Shift query demo, block statement. So we have all of these block statements. Oh, because this is a body. So all bodies. Yeah, we'll have to have a couple of these because these are bodies that have a block in them. Let's see, function body or body. So yeah, we have a function body here that has a statement, that has a block statement that we don't need. So we would need to get rid of that block statement. So let's see, block statement. Will this work? Ooh, this will. All right, that'll get rid of that. So now let's look for function bodies that have no, we want that, don't we? Let's see what happens if we replace that. Return node statements 0. This doesn't strike me as, I'm not even really thinking here. I'm just operating based off of assumption, which is sometimes how my brain works. Like I get into the point where I'm actually thinking properly, and then I reach some sort of point where I just start writing code and running it and seeing what happens. Yeah, that doesn't work. Yeah, we could have predicted that together, couldn't we? Oh well. All right, so what are we getting here? We're getting all the block statements that have a parent of function body. So we have a block. So this is, the problem here is because function body itself has statements, doesn't it? Yeah, so function body itself has statements, and the problem here is that we also have a block statement which has statements. So what I need to do is get the, so we have the block statement, block statements. So we need to replace function body statements with the block statement statements. Okay, so we actually need our function bodies that have a block statement. Can we do that? Can we write a query that does that? So we need the parent. We're not going to be able to do that. Do we need to do the function body, and we need to go through all the function bodies and figure out whether or not we have the right block statement? Is it worth it? Let's see. All right, so we are selecting the function bodies here. We're going to iterate over all the function bodies. Query. So this will get all the function bodies. Want to filter which bodies have in them just a block statement. Body dot statements dot length equals 1, and body statements 0 dot type equals block statement. Let's see what we get out of this. All right, so we get 3 function bodies. Is that what we're looking for here? So we got this one, which is dumb, this one, and that one. All right, so that's what we're getting. So now what we want to do is refactor.replace dumb bodies with So we want to replace the bodies with the statements of its child block. So let's see, we're going to make that less ugly. So node dot statements equals node dot statements 0 dot block. So statements block as type block, and then the first statement's there, statements. Okay, so we are not actually replacing anything there. We're just iterating over all these, so I'm going to return the node. I'm not sure if I have a for each in shift refactor. Probably should. No. Shift refactor. What version is latest? That is latest. That's a shame. I don't know what the problem is here. Anyone able to quickly assess the code right here? So we're placing dumb bodies. So this is a list of stuff, and we should be able to pass in a list of nodes there. I'm pretty sure that is supported, though I guess it's not. Node deobfuscate. Input.charcode@ is not a function. So shift, oh, the parser. So it is trying to, it's trying to read that as a query because this is an error coming from shift query and not shift refactor. That's unfortunate. All right, well, I gotta add a bug there. All right, well, I don't really need refactor there anyway. So dumbbodies.for each node the reason why I don't need refactor there is because I'm just iterating over the nodes and writing out or modifying them in place. Cool. So we have replaced the block statements there. We still have block statements over here, but the functionality is going to be largely, or the strategy of getting rid of those is going to be largely the same. So we can skip that. Actually, this marks the finale of reversing JavaScript obfuscator. We have gone through every single obfuscation that exists and have reversed it. Compact is nothing too exciting. Control flow flattening we went through last time. Dead code injection we went through this time. Debug protection we got rid of. Disable console output. You know what? I'm not sure we actually touched that. Let's see what it looks like. Let's see here. Disable console output. Node obfuscate. Let's see here. So it looks like it adds this blob of something up here and just overrides all the console functions with L. What's L? L is nothing. Okay. Yeah, this actually, I hope if you've been following along at this point, given the number of things that we have reversed, this is not even worth looking at because all we need to do is just remove this, remove all of it. None of this. So if we got rid of this and then ran our code, it's still going to work. So, well, you know what? Let's do it. So this is, let's see, 1, 2, 3 statements out of the iffy that we need to delete. We have other code here. All right, let's try to do them. Well, you can look at one of the older streams because what the problem right now is that if I try to enable all the obfuscations together, it's going to throw other wrenches into it, which I'm not going to be able to get done by the end of the hour. But the gist of this here, if you want to do it yourself as an exercise to the viewer, is you would go to deobfuscate and basically just delete the statements that you want to delete, and you're done. That would be removing or completely nullifying this console log obfuscation or protection. Disable console output. Anything that strictly adds code to script in order to protect it one way or the other is trivially bypassable just by literally removing it. We went through this last time. I think it was the either stage 3 or stage 4. There were a few fairly elaborate protections in place. But at the end of the day, all you had to do was just delete the code in order to bypass them. And some of the protections actually just reduced performance substantially. So that type of protection for JavaScript is just not effective at all. In order to effectively protect JavaScript, you have to destructively modify the original source JavaScript so that it can't be translated back to its original form. And even with the obfuscations that we've seen so far, the dead code injection and the control flow flattening, we've been able to reduce those fairly easily because it is so hard to actually modify JavaScript and protect it effectively. All right. Well, I have some tasks for me here. I need a notepad. So I've got much more work to do on Shift Interpreter. And what was the bug we came up with? It was, the Shift refactor was not taking in a list of nodes effectively. I will take care of that immediately because that is annoying. And I felt like I run up against something similar before, and we need to get past that. So cool. Thank you very much. Appreciate you tuning in. If you're interested in this stuff, follow me on Twitter at JSOverson. You can subscribe to this channel. I'm doing lots of JavaScript-y manipulation stuff. A lot of the concepts that we've gone through in this series so far, I'll be translating into proper videos, actually just about now, because we have gone through JavaScript-obfuscator obfuscations, and I will convert all of that content into the easily consumable videos. So thank you very much, and I'll talk to you next time. Later. Now, how do I get off of this thing? Bye.